Okay, so for today's lesson, we're really trying to answer the question, how does a cup's surface affect how light warms up a liquid inside of the cup? Remember, we talked about light and heat and maybe how it interacts with our cup system in the previous lesson. And today we're going to be doing an experiment, so hopefully we understand a little bit more about this interaction. So first, I want you to think to yourself or turn and talk to someone around you. What were some of the ideas from the last class about how light could be affecting the temperature of the water inside the clear plastic container? What were some of the ideas that you captured on your initial model? So, the point of our experiment that we're going to be doing today, and kind of the question we're trying to answer, is how water inside the cup is warming up when it's in a closed system. And remember, a closed system means that no matter is entering and no matter is exiting. And so we think light might be having an effect on what's causing our water or our liquid inside of our cup to warm up. To broaden our understanding of this idea or the role of light, um, we need to think about different cups or different materials that these cups could be made out of. Let's make a prediction. Looking at these cups here, these are different than the cups that we have been working with. Our normal cups have been clear, or a fancy word for that is transparent. Transparent means that I can see right through it. But these cups here, they're colored. They're called opaque. That means that I cannot see clearly through the cup. So, do you think that light would affect water in these cups the same way as a clear plastic cup? Would it be different if our cup was transparent versus opaque? So, thinking about whether it's transparent or opaque, do you also think the color or the color that our cup is painted might affect how the liquid inside warms up? We see that there's a lot of different colors of cups here. And so maybe color might also play a role in determining how the light affects this liquid. Okay, so today we're going to be doing a science experiment. We're going to be shining a light on some different cups. As you can see here, we're going to have a foil cup, a cup that's covered in tin foil. We'll have a clear plastic cup. We'll have a white painted cup and a black painted cup. And the whole goal of this experiment is to answer these two questions. Does light affect the temperature of the water inside of the cup system? And how does the cup surface affect how light warms up the water inside of the cup? Okay, so we didn't do this lab here because I don't have the materials with me where I'm not able to set them up. So you're gonna have to look for a different video to explain what happened in that lab. But I do have some data that I collected here that I can share with you guys. So our starting water temp in this experiment was 10 degrees Celsius, and our air temp around the cups was 22 degrees Celsius. This makes an interesting observation because we noticed that the water temperature is quite colder than the air temperature around the cups. Additionally, we set up two experiments. Remember, one of them was light. That means we were shining a light on these cups. And the other was our control. This was our dark group. Let's look at our light experiment first. For clear, our temperature rose to 14.5. Our foil rose to 11.6. Our black cup rose to 14.1, and our white cup rose to 12.6. Now, because they all started at the exact same water temp, we can use these numbers to analyze them, but typically the water temp isn't always going to be the same. So it's helpful for us to calculate the delta T. Delta, this triangle symbol, is just a fancy science term or math term for change. So we're measuring the change in the temperature. So we take the final minus the initial. If we take 14.5 and we subtract 10, that gives us a delta T of 4.5. I'm going to highlight this because this is the number we're really focused on. For our foil cup, we have 11.6. If we subtract that by 10, we get 1.6. Our black cup, if we subtract 14.1 by 10 degrees, we get 4.1. And for our white cup, if we take 12.6 and subtract 10, we get 2.6. Our dark group, if we subtract 11.5 from 10, we get 1.5. If we take 10.9 minus 10, we get 0.9. If we take our black cup 12.2, we get 2.1. And then our white cup 11.9, that gives us 1.9. Looking at this data, I noticed some interesting observations. Number one, our dark group, all of them still increased in temperature. Now, it might not be a lot, but it still has a notable increase in temperature. So that means that light isn't the only factor here. There must be something else that's warming up the liquid inside of our cup. But when we're looking at our light conditions, it definitely increases the temperature of our liquid. Our clear cup has a temperature change of 4.5. That's pretty high. Our black cup has a temperature change of 4.1. That's also fairly high. Foil's pretty low. It's only about 1.6. And then our white cup has a temperature change of 2.6, which is a little bit higher, but still relatively low. As we did this experiment, we also took some data about the incoming, transmitted, and reflected light, and I want to share that with you now. So our incoming light for the clear cup was 103. Our incoming light for the foil was 56. Our incoming light for the black cup was 54, and our incoming light for the white cup was 23. Now, ideally, we do want all of these numbers to be the same, but I lined all four cups up in front of the lamp. So inevitably, some of them are probably going to get more light than others, which is accounting for these differences. Let's talk about the amount of light transmitted. This is when I put the sensor inside of the cup to see the light going through our material. For clear, I got 90. For foil, I got 1. For black, I got 0. And for white, I got 6. Next, we can talk about the amount of light reflected. That was the light that bounced off of our cup. I measured that by holding the sensor towards the cup. For clear, I got 9. For foil, I got 11. For black, I got 3. And for white, I got 4. Now, here's the problem. I have all of these numbers and I'm really focused on the transmitted and reflected, but unfortunately, they all had different amounts of incoming light. So that's not providing me a very meaningful way to compare these numbers. So what I'm going to do is I'm going to take a percentage. I'm going to say how much of our total light, our incoming light, was transmitted. How much of our total light, our incoming light, was reflected? And then obviously the last interaction that light can have with matter is being absorbed, but we can't directly measure that. And we'll discuss that in a second. So what we can do is we can use this formula that I have right down here. We can take the amount of light transmitted divided by the amount of incoming light, our part over the whole. And remember, whenever we do a percentage, we're also going to have to times by 100. So let's do some of these calculations now together. I'm going to do the transmitted first for the clear. So I'm going to take 90 divided by 103, and then I'm going to times by 100. And that gives me roughly 87%. Now, if you want to round to some decimal places, it's 87.3786. You could maybe round it to 87.4, but I'm just going to round it to 87. Then we'll do our transmitted for foil. I'm going to take 1 divided by 56 times by 100. And that's going to give me about 2%. Again, if you want to be really specific and round to the first or second decimal place, go ahead. For black, it's 0 divided by 54. Well, hopefully we know that 0 divided by anything is going to equal 0. So our transmitted light for the black cup is 0. And then we're going to take 6 divided by 23 times by 100. And that should give me 26%. 26%. Now let's do the same thing for reflected. I'm done with my transmitted column. Now we're doing reflected. So let's start with the clear cup. I'm going to take 9 divided by 103 times by 100. That gives me 9%. Now, here's the question to think about. Okay, we have the amount of light transmitted, we have the amount of light reflected, and we're missing one, the amount of light absorbed. Notice that if we took 87 plus 9, that doesn't equal 100. And whenever we're doing percents, it should always equal 100. That difference there, the amount of numbers we're missing to get up to 100, that's our amount absorbed. So we could take 100 minus 87 minus 9 and get the amount of light absorbed. Let's do reflected for foil. So I'm going to take this 11 divided by 56, 11 divided by 56 times by 100, and that's going to give me about 20%. Then we can do 3 divided by 54 times by 100, and that gives me 6%. And then we can go 4 divided by 23 times by 100, and that gives me 17%. Okay, so we have a bunch of data. I want to collect this all in one table so that it's a lot more easy to understand. So I'm going to just transfer these numbers down here. One thing to keep in mind is my black and white columns switch. So that's something I'm also going to have to switch over here, which is fine. I can do that. Okay, so those should be locked in. And then I need to transfer my delta t's that I had up here. We'll do our light first. And then we'll do the dark group. Remember, my black and white are switched, so I'm gonna have to remember to switch those numbers. I don't know why it's set up like that. It'd probably be better if it was all the same. Okay, this is where we need to construct a notice and a wonder chart on a blank sheet of paper because we need to analyze what this data is telling us, okay? So construct a T-chart and you're on a blank piece of paper. On one side, put notice, on the other side, put wonder. I want you to take some time by yourself right now. Look at this data. What do you notice? What do you wonder? As I'm looking at this data, let's look at the dark group first because it's just the easiest one to talk about. Notice with our dark group, all of the cups are increasing in temperature over time. All the liquid inside of the cups is increasing in temperature. This is telling me that there must be something else to this. It can't only be impacted by light. Obviously, light is a factor, it's a part of it, but there's something else. Even in our dark condition, the temperature of the liquid inside the cup is still warming. Now let's look at my light conditions. First, I noticed that the clear cup, it changes temperature a lot. I notice it has a really high amount of light that is transmitted. I see that there's little amount of light that is reflected. So let's think to ourselves, why would the clear cup possibly be increasing the temperature of the liquid over time? Maybe it has to do with the amount of light being transmitted, and that transmitted light can reach that liquid and warm it up somehow. Let's look at the black cup. The black cup also had a high temperature change, but zero amount of light, 0% of light was transmitted, and zero. Let's also look at the black cup because it had quite a high temperature change as well. We see it's around 4.1, which is just a little bit less than the clear cup. But the light is very interesting here. We have 0% of light that is transmitted or going through the black painted cup. We have only 6% of light being reflected. So where is this other light going? And as we discussed, light can interact with matter in three ways. Number one, it could be transmitted. Number two, it could be reflected. And number three, it could be absorbed. So we know that most of the light here is being absorbed. Maybe that absorbed light is heating up or warming up the liquid inside of that cup, accounting for that 4.1 temperature change. Let's look at the white cup next. It had a little bit of a temperature change, definitely not as drastic as the clear or the black cup, but we notice that there's 26% of light transmitted, 17% of light reflected, and then the rest would be absorbed. So again, maybe that combination of the absorbed and transmitted light is helping to warm up the liquid inside of our cup. This one's interesting, the foil. With the foil, we have a really small temperature change of only 1.6. We notice that 2% is being transmitted, that's barely anything, and 20% is being reflected. That's the most being reflected. This makes sense because foil is a shining surface. And when we think about shining surfaces, we often think about them being a reflection. We're reflecting light. But most of our light is being absorbed. So maybe we need to question about, is absorption really affecting the temperature change in this liquid? I'm not sure. I'm not fully convinced based on the data that is right here. But definitely the transmitted light is affecting our clear cup. That makes sense because it's clear. The light can go straight through. Our black cup, most of the light is being absorbed. These are things to think about as we move forward. Okay, so to kind of summarize what we've been doing so far in this lesson, we did an investigation where our focus was on answering these two questions. Number one, does the light affect the temperature of the water inside of the cup system? And number two, how does the cup surface affect how light warms up the water inside of the cup? I want you to just think to yourself for a second. What was the purpose in our procedure? What was the purpose of testing the cups in the dark? What was the purpose of testing these different cups in the light? Hopefully, we're able to see at this point that the purpose of testing the cups in the dark was to have a comparison. We're wondering the impact of light. So, obviously, we need a control group so that we can compare it to. Obviously, we'll have cups in the dark. And then the purpose of testing the cups in light, that's the whole point of our experiment. Does the light affect the temperature of the water inside of the system? If we have different cup surfaces, like a black painted cup, a white painted cup, a foil cup, a clear cup, is that going to affect how light interacts with our cup system? Okay, so hopefully you've been following along as we've been collecting our data and analyzing what it could possibly mean. Now, I want to take some time to draw some models. We've been practicing this skill. Models are extremely important in science, and I want us to base our models off data. In science, we can make claims, we can say things, but if we don't have data to support what we're saying, then it's what we're saying isn't valid. There's no value in it. So hopefully you have the data written down from your previous procedure or previous investigation. So we're going to be explaining temperature changes in different instances. We have a key here. I'll talk about it as we go through it. But first, let's focus on this clear plastic cup. This was in our light experiment. Think about the light and what happened as it reached that cup. Right here, we can see the incoming light. Right here is our, I'm going to label this incoming light. This is the light that we are shining on our uh, Now, the question becomes, what can happen to this light and what happened to most of this light? If we look at our data, we see that most of this light was transmitted. It went completely through the cup wall. Right here, we can see the cup wall. So what happened to most of this light? It went completely through into the inside of our cup. It was transmitted. Transmitted. Now, not all of it was transmitted, though. Some of it was reflected, and we can represent that with maybe a smaller line saying, hey, not all of it was, but some of it was transmitted, and then a little bit was absorbed. Absorbed. Reflected over here, it bounced off of the cup. And then we also know that some of it was absorbed, but most of it was transmitted, which is what we demonstrate here. Now, if we're thinking about the clear plastic cup in the dark, well, If there's no light, what's going to happen when it interacts with the cup? If there's no light, no light, so there is no interaction. There's no light present, it's not going to interact with the cups. We get this question below. How did you explain why the clear plastic cup in the dark was different from the other cups? It's different and similar in kind of two aspects. It's different because there was no light. We did not shine light on this cup, and therefore light was not a factor. However, the liquid inside of the cup still warmed up. Thus, something else besides light must influence the temp of this liquid. Something else must be influencing the temp of this liquid. This is our first set of models. Hopefully you're following along. I represented the incoming light, the light that I shined on my cup. Most of it was transmitted. I demonstrated that with a thick arrow. Some of it was reflected, and then some of it was absorbed. Let's go on to the next one. Okay, so now I have some more models. I have the black cup and I have the white cup. I want you to take a second and try to do this by yourself. How would you represent the light being transmitted? How would you represent the light being reflected? How would you represent the light being absorbed? Take a second and try to do this by yourself. Okay, hopefully you attempted this by yourselves. I always want us to attempt. I don't care whether it's right or wrong, but attempting is trying, and trying grows your brain muscles. So remember, this line right here is representing our incoming light. Incoming light. I'm going to label that just so it's clear. Incoming light. Now, if I look at my data table, where is most of this light going? When I'm looking at the black cup, I notice that zero is being transmitted. None of that light is making it through the wall of the cup. I know that 6% is being reflected. So yes, some of it is being reflected, but a very, very small amount. Well, Mr. Mayman, that's all I have left on my data table, so I don't know where else that light is going. Remember, light can interact with an object in one of three ways. Number one, it could be transmitted. Number two, it can be reflected. And number three, it can be absorbed. So most of this light is being absorbed within the walls of the cup. So here we have a little bit of light that's being reflected. And here we have most of our light being absorbed. Let's focus on the white cup. For our white cup, again, we have the light that's incoming, the light we're shining on our cup. Just going to copy that over. So then where is most of this light going? If I look at my data table, I see that 26% is being transmitted. That's a pretty high number, but not super high. So maybe I'm going to represent that with like a medium line. Some of that is going to the other side. It is being transmitted. 17% is being reflected, a little bit less, but still not very high, is being reflected. So if only a little bit's being transmitted, if only a little bit's being reflected, where is most of it going? Most of it is being absorbed into the cup itself. Most of it's being absorbed. So again, I have a little bit that's reflected. I have a little bit that's absorbed. And then most of it, I have a little bit being reflected, a little bit being transmitted, most of it being absorbed. So this brings me to my question down here. How did you explain how the water in the black painted cup warmed up compared to the water in the white painted cup? So this is talking about the temperature difference in the cup. First, I'm going to state directly from my data. From my data, the liquid in the black painted cup warmed up more compared to the liquid in the white painted cup. This is a fact from my experiment. This isn't something that I would argue with somebody. This is coming straight from my data table. 4.1 is a higher number than 2.6. And let's think about why might that be happening? Be why might the liquid in the black cup might be like warming up more compared to the white cup? And I think it comes down to this idea of absorption. Absorption. We're absorbing a lot more light in our black cup compared to the white cup. The white cup is also absorbing some of that light. It is transmitting some of that light. But what ultimately is going to come down to this is that the black cup is absorbing most of the light. Somehow, this light energy is being converted into heat that is my warming the liquid inside of the black cup. Again, we look at the data in front of us, we make some claims, and we make some conclusions. Okay, we have one last model that we have to do, and this is for the foil cup. Again, I want you to try this by yourself first. Remember, we need to show three instances of light interacting with our cup, transmitted, reflected, and absorbed. Again, hopefully we tried something. Right here, we see our line. This is the incoming light, the light that is being shined on our incoming light. When I look at my data table, most of the light is being absorbed. How do I know this? Transmitted, it's only 2%. This is basically nothing. Basically, none of my light is being transmitted or going through that foil. When I think about reflected, 20% is being reflected. That is quite a bit, but it's still not a lot. 20% is being reflected. So that must mean most of the light here is being absorbed. Remember, we have reflected, transmitted, and absorbed. So then how do you explain how the water in the foil covered cup warmed up differently compared to the other cups? Note that the foil covered cup did increase in temperature. Maybe we should say, note that the liquid in the foil covered cup did increase in temperature. I didn't spell that right. Temperature. However, it did not increase drastically. It didn't increase a lot. However, what we can see from our model here is the foil cup had the most light reflected. This makes sense because the shine foil uh, shines or reflects the light. Additionally, most light is absorbed, so it would make sense that the liquid inside of the cup would increase in temperature. This is what we can add to our model. This was our final question. So hopefully going over all these models, thinking about our data and what it means, this paints a little bit more of a clear picture. Okay, so the last thing that we need to do today is we need to update our progress tracker. Remember, what's the point of a progress tracker? We're trying to track progress. You're not going to remember all of the things that we've learned from this unit, like the information we learned on day one. So, this is your opportunity to write down these important thoughts so that you can capture them for when we have a summative or a formative assignment assessment, and you can use this information to help refresh your memory. So, we're focusing on today's question. How does a cup's surface affect how light warms up a liquid inside of the cup? So I want you to write down what you figured out in that column. You should be writing about two things. Number one, how is light interacting with these surfaces? Number two, how do different materials that the cup's made of impact how the water inside of that cup warms up? How does that idea connect to what we've been learning about light? So take some time, update your progress tracker, make sure you're capturing these ideas. So that concludes our lesson for today. Today we've really been focusing on light, but there's another aspect to this, the other aspect of your initial model from lesson 7, and that's heat, which we're going to explore in our next lesson.